Generally in physics 30, when we see an exam question involving electromagnetic radiation or any other concept, we don't usually have to remember somebody's name that's associated with it, but every once in a while we do. We're talking about electromagnetic radiation right now. Who's the guy that came up with the theory that first described electromagnetic radiation? What's his name? Remember, I'll give you a hint. Scottish guy. One of the only Scottish guys that we see in physics. Yep. Maxwell, James Clerk Maxwell. Maxwell came up with a theory that something causes electromagnetic radiation. What is that thing, that one tiny little thing that is the cause of every type of electromagnetic radiation? Jacob? No, electromagnetic waves are electromagnetic radiation. So what's the cause of electromagnetic waves or electromagnetic radiation, Hugh? Motion of what? Carrie? No, not motion of energy, no. Austin? Yeah, okay, it's good. Motion of electric charges, but let's be a little bit more specific there with motion. Motion of electric charges, assuming the electric charges are going with uniform motion, okay, then those electric charges will produce a gravitational field because they have mass, an electric field because they have charge, a magnetic field because they have motion, but not electromagnetic radiation. What's the special condition that those moving charges have to possess to produce EMR? Gary? No? No? Good, they've got to be accelerating. So we're going to say accelerating charges generate EMR. Not just charges, not just moving charges, but accelerating charges produce EMR. Now, the reason it requires accelerating charges to produce EMR is because accelerating charges produce changing electric and changing magnetic fields. You guys remember that EMR consists of sinusoidal electric and magnetic fields that are perpendicular to each other. It's going to look something like this. It's hard to draw, so bear with me here. That's brutal. You get the idea, though. We get a sine wave electric field, a sine wave magnetic field. They're going to be perpendicular to each other. And the only way we can get those sine wave magnetic and electric fields is if we have the accelerating charge. A moving charge with uniform motion is going to produce an electric field and a magnetic field, but they're going to be constant values of electric and magnetic fields. And that's not what we want for EMR. Why not? Why not? Why is it important to have these sinusoidal waves? Well, if I have an electric field wave that looks like this, we'll call it E1, and a magnetic field wave that's on a different axis that looks like this, we'll call it B1. Well then, in order to get a B2 and an E2, then we have to have these changing values. Maxwell said that a changing electric field will produce a changing magnetic field. So E1 produces B2. And a changing magnetic field will produce a changing electric field. So we're going to say that B1 produces E2. In order to get this new field that propagates, that moves this way, perpendicular, by the way, to both the electric and magnetic field, we have to have a changing E1 and changing B1. If E1 was constant and B1 was constant, then that's fine. Okay, they're there, but they're not going to produce E2 and B2. And that's what we need to have EMR. All right, by the way, unless the charged particle is still accelerating, still causing more magnetic and electric field, then those guys are gone now, right? Okay, their energy was transferred into E2 and B2. What happens now? Well, E2 will produce, this is when the diagram is going to start looking even worse, but you guys remember what the diagram is supposed to look like, right? E2 will produce B3. And B2 will produce E3. Well, once again, the energy that was present in B2 and E2 is gone. It was transferred to B3 and E3, and then we have the wave looking like this. So we started with a wave over here, accelerating charged particle produced B1 and E1, and then the changing nature of those magnetic and electric fields caused it to propagate to the right, perpendicular to both the electric and magnetic field. So that's why it's critical that we don't just have a moving charge. That's why it's critical that we have an accelerating charge, a charge that produces a changing electric and magnetic field, as opposed to just a regular uniform electric and magnetic field. All right? There were 4 properties of waves that are exhibited by electromagnetic radiation. 4 properties of waves that are exhibited by electromagnetic radiation that show us, that provide support for Maxwell's wave theory of EMR. You guys remember what those 4 things were? Those 4 wave properties are? One of them is, I don't care what order you give them to me, by the way. Yeah. Polarization. Remember, polarization is that phenomenon whereby part of a wave gets filtered out. Here we had a really simple polarizing filter is a piece of plywood with a slit cut in it like this. And if you've got a string that goes through that opening, through that slit, and you're flinging it up and down like this to produce a vertical wave, then it gets filtered out. That vertical wave doesn't go through this horizontal opening. But if you have that string that you're flicking horizontally like this, producing a wave that looks like this, then the whole thing goes through. If you're flicking it like this to produce that wave at an angle, then the horizontal component of that wave goes through. So in the end, you're polarizing that wave horizontally. You've got a filter that allows only one component of a wave to go through. Now, this happens obviously with a piece of plywood and a string, but it can also happen with certain filters like plastic or glass filters as well that are etched in a certain way. Certain properties of the glass, certain properties of the plastic that can cause polarization as well. Polarization is a property of waves. It's a property that's exhibited by EMR, so EMR must be a wave. That's another one. That's the hardest one, by the way. Jacob's the guy this morning, eh? Jacob? Diffraction. Diffraction is the spreading out of a wave. Goes to an opening, it spreads out. It's a property of waves. It's exhibited by EMR, so EMR must be a wave. Third one? Okay, it doesn't matter what order you give them to me in. Yeah, Caitlin? Interference, good. If you guys remember from physics 20, when you got a wave, got another wave, 2 waves, they encounter each other, we can make a bigger wave or a smaller wave. If the 2 waves come together and make a bigger wave, it's called constructive interference. If they make a smaller wave, then we call it destructive interference. Well, that's a property of waves. EMR exhibits that property, so EMR must be a wave. Finally, what's the 4th one? The last one? Good? Good. Refraction. Refraction is the bending of a wave. We're going to talk about this in more detail later on in the unit. But basically, when a wave goes from one medium to another, it changes speed, always. It either speeds up or it slows down. And as a result of that speeding up or slowing down, it's going to change direction. That's called refraction. That's a property of waves, but it's exhibited by EMR, so EMR must be a wave. Finally, we talked about the electromagnetic spectrum on Thursday. Played that song to help you remember radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And we ranked them in terms of frequency, wavelength, and energy. We know that radio waves have the lowest frequency, the lowest energy, and the highest wavelength, whereas gamma rays, it's exactly the opposite, the highest frequency, the highest energy, and the lowest wavelength. Let's refresh our memories as to how each of these types of EMR are generated. Radio waves and microwaves are both produced by, you guys remember this? Watch my finger. They're both produced by what? I'm not trying to hypnotize you here with my finger. I'm trying to give you a hint. What's my finger doing right now? Oscillating. It's going back and forth, right? These are both produced by oscillating electric charge. infrared, visible light, and ultraviolet. And occasionally X-rays can be thrown into the mix for that as well, but not usually. Infrared, visible light, or ultraviolet are all produced by electrons on higher levels in atoms, and they fall to lower levels, transitions of the electrons in atoms. We're going to talk more about this in our last unit in about 3 weeks. Different transitions result in different frequencies of EMR that are given off. Different transitions in different atoms result in different frequencies of EMR that are given off. X-rays are produced by rapidly decelerating electrons. What happens there is that electrons are accelerated to incredibly high speeds by a potential difference. That would be an EI equals EF problem, right? Okay, potential energy causes these electrons to speed up to an incredibly high speed. Potential energy converted to kinetic energy, and then they smash into a target and they decelerate. They stop almost instantly. Well, the kinetic energy that they gained when they accelerated has to go somewhere. It goes off in the form of an X-ray photon. Finally, gamma rays, they're produced by nuclear decay. We're going to talk more about the last 3 ways of producing EMR later on in this unit or in the next unit, depending upon which one we're talking about. Nuclear decay is something we deal with almost at the end of Physics 30. In nuclear decay, what's really happening there is matter, mass, is changing into energy, according to a little trick that Einstein taught us just over 100 years ago. Finally, I told you the bad news on Thursday is that you got to remember the frequency, wavelength, and energy ranges of all 7 types of EMR, 21 different ranges. But the good news is, really all you got to remember is 3 different frequency ranges and then find the rest from that. Microwaves, you guys remember the frequency for microwaves? 10 to the 9 to 10 to the 12 hertz. X-rays, we'll go with X-rays next. 10 to the 17, 10 to the 20. You guys might not remember these right now, and that's okay, but you got to remember them. Okay, I'm not asking you to remember all 21 different ranges. I'm asking you to memorize 3. I think we can handle that. Okay, 10 to the 17 to 10 to the 20 hertz. And finally, visible light. We want to be a little bit more specific with this one. This is 4 times 10 to the 14 to 7.5 times 10 to the 14 hertz. If you have a frequency that's 10 to the 13, it must be infrared. 10 to the 22, it must be ultraviolet. 10 to the 7 must be radio waves. If we have a wavelength of 6 times 10 to the negative 7 meters, well, then we can find its frequency by saying V over lambda. And then we can say, well, I know what its frequency is. 5 times 10 to the 14 is visible light. So regardless of whether we're given any of the 7 frequencies, we can compare it against our 3 memorized ranges. Any of the wavelengths, we can find the frequency, compare it against any of our memorized ranges. And then energy, do the same thing as you did for wavelength, except you just haven't learned the equation yet to do it. That comes later in the unit. Right? Let me give you a couple multiple choice questions here, starting with there's actually a few multiple choice questions I want to give you. Starting with questions number 97 and 105. I'll ask you to take a look at both of those right now for the next about 3 minutes, and then we'll take a look at both of them when you're finished. All right, question number 97. EMR is produced by charged particles that are moving. What's the answer to that question? C with a changing velocity, right? With accelerating charged particles generate EMR. I could change that question. I could change that question to say magnetic fields are produced by charged particles that are moving with zero acceleration. Yeah, but that's not the question here. Maxwell's work number 105 contained the new idea that, what's the answer to that one? What's the answer, Nick? It's C for that one as well. An electric field that changes with time generates a magnetic field. We also know that a magnetic field that changes generates an electric field. Okay, a couple more questions here. Or one more question right now. Gamma radiation can be produced by what? We'll just do this one together right now. Gamma radiation can be produced by A, radioactive decay, nuclear decay, radioactive decay, matter being converted to energy. I'm going to ask you to do number 100 right now. I'll give you about a minute to do that one. All right, let's have a look at this one now, please. It says selected regions of the electromagnetic spectrum: television, AM radio, gamma radiation, ultraviolet, visible light. The last three make sense to us, but television and AM radio? What are those? Well, you guys remember the video? Okay, so from your TV station to your living room, right? That's radio waves. Okay, so television is radio waves, but which one comes first, AM or TV? It's kind of like the colors of visible light, right? Roy G. Biv, there's different frequencies, different subcategories within visible light. There's different subcategories within all the other types of EMR as well. We just don't memorize all the rest of them. Okay, radio waves fall into television and AM radio. Let's write these down here. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Okay, that's in terms of increasing frequency. Increasing wavelength, we're going this way. Okay, so let's identify what we've got here. Okay, gamma radiation is going to have the lowest one, so that should come first. Okay, X-rays, I don't see that. UV, that's going to be the next lowest wavelength, or the next highest frequency. Visible light comes next, and then we've got radio waves. Which one is which? Well, here's the good news. If you recognize that gamma comes first, then the answer has to be either A or C. Then ultraviolet comes next. Well, then the answer has to be C. We don't have to be able to distinguish between radio waves, AM radio waves, and television waves. If you did, you would find that AM radio waves can't spell radio, but AM radio waves come before TV in terms of frequency or after TV in terms of wavelength, but you didn't need to know that, okay? You need to know this and the subcategories of visible light, but things like this you can come up with based on the question itself if you ever see a situation like that. Here's one more. Number 102, please. Let's have a look at this one now. Sources of EMR. Movement of outer electrons to lower orbitals. What we want to do in a question like this is like what we want to do in a lot of questions that we see, and kind of look at big picture. What do we know about this before we actually see the question? Movement of outer electrons to lower orbitals, we know that's going to produce either infrared, visible light, or ultraviolet. Okay, deceleration of high-speed electrons, that's going to be X-rays for sure. Decay of radioactive nuclei, that's going to be gamma rays, nuclear decay. And rotation of an armature in a generator. A generator produces electric current, right? If it's an alternating electric current, an AC current, then it's going to be oscillating electric charge, which means it's going to be radio waves or microwaves. Specifically, if it's like true electric current from a generator, it would actually be radio waves. All right, so what do we got here? Gamma rays are going to be the third one. Visible light looks like it's going to be the first one. X-rays are going to be the second one. I don't like this term, but we can work around it because, again, we can figure it out by process of elimination. Extremely low frequency wave, that's a radio wave. I just don't like it when they call it that, because in the end, that's more about how it's caused as opposed to what it's actually called. You could consider that to be a subcategory of radio waves, extremely low frequency wave. But in the end, AC is a current, not so much a wave. Okay? We're going to call this a radio wave, which means it's going to be number 4, 3124.